Welcome to afternoon session at our Cyber Tech and Risk Security Automation virtual conference. Our next speaker is Kieran Miller. Kieran is the chief architect at Garantir, a cybersecurity company based in San Diego, California. With over a decade of cybersecurity experience, Kieran has expertise in multiple dimensions of enterprise security, from data security, identity access management, to secure software development and network security. Kieran has a lot of insights you can learn from him. And Kieran will talk about a novel approach to automating security credentials. Kieran, all yours.
Thanks, Brian. Pleasure to be here. That's quite the introduction. I hope I live up to it. So today we'll be talking about automating secrets management at scale. And we're going to interpret the automating on two sides. So one is we want to automate the security controls when we're doing secrets management. And then the second is we want to apply that to automated environments where the applications are not run with human users behind them. So applications require secrets for a variety of use cases. Authentication, authorization, and data protection are some of the most common. Now, when a human user is using the application, you can offload a good part of that secrets management to the human. The human can memorize a password. They might have external devices like FIDO2 devices. You can use biometrics. There's a number of ways to do that. But when the system is fully automated, when there's no human user behind it, the problem has to be solved a little bit differently. And that's what we'll talk about. We'll emphasize more here today. So the first approach to this was not a very good one. It's called Hardcoded Secrets. And basically, we're just embedding the secrets into the application. So this is easy to steal the secrets. You can decompile the application. If you get your hands on the source code, you can view that. There's a number of ways to do it. And it also had the byproduct that it's hard to rotate secrets. So since the secret's embedded in the application, it would require you to deploy a new application in order to rotate it. And even though some other techniques like obfuscation techniques like base64 encoding and all that were used, they don't help much. An attacker can easily get past all that. This is basically well documented. It's just bad practice. So we moved forward as an industry and we realized, okay, we need to separate the secrets from the application. And the way to do that is you have the application read the secrets from a specified location at runtime. The two most common approaches for this are configuration files and environment variables. Now, we got some pros out of this. So now decompiling the application no longer reveals the secrets, and secret rotation doesn't require us to deploy a new application. However, we didn't solve all of our problems. So we don't have any central management or visibility on all secrets in the enterprise. And we don't have, or the secrets are now available in plain text format to the application. So meaning the application actually gets the raw bytes of the secret. So if the application gets compromised or it's running in an environment that gets compromised, then the secrets are effectively compromised. There's also limited security controls between the application and the retrieval of the secrets. So the next approach was to use a secrets manager. And that is a dedicated service that stores secrets and grants access to them programmatically. Now, the application or a user, if it's a user can use it too, authenticates and then retrieves the secrets that it has access to. So on the pros, we have all the pros from before, plus two new ones. We now have central management and visibility on each time the secret is exported. And there's more security controls possible before the application gets access to the secrets. Now on the cons, we still have that secrets are available in plain text format to the application. So you may notice I emphasized the secret being exported. So basically we're grabbing the secret and then the application gets the raw byte, access to the raw bytes again. We also have some other issues. We don't have central visibility on each time the secret is used. We can have visibility on each time the secret is exported, but once I export the secret, maybe it's an API key and during the lifetime of the application, I use it 100 times. I won't see central visibility on that. You may be able to scour some logs across the enterprise and kind of correlate it, but you're not going to have one single place to easily look at that. There's also, we're unable to enforce security controls each time the secret is used. Again, this is having to do with the fact that the secret is exported. You can enforce the security controls the first time when the application authenticates, but after the application authenticates, it can just use that secret as much as it wants once it has it exported into memory. We still require security credentials to the secrets manager. So we have to authenticate ourselves. So those are typically still stored in environment variables or something like that. And then lastly, we still require to rotate secrets frequently because we're exporting the secrets into an area that could be compromised. We have to rotate the secrets as a compensating control. So can we do better? So by that we mean, is it possible to do secrets management and meet these requirements? So the secrets not being available to the application in plain text format. So the application wants to use the secret, but can we do that in a way where it doesn't get access to the raw bytes of the secret? We want central visibility every time the secret is used. So as opposed to just when it's exported, we'd like to know every time that secret is used. We'd like to enforce security controls, optionally if you'd like, every time the secret is used. So for example, in an end user case, maybe every time they use an SSH key, you want to enforce multi-factor authentication every time. Can we do that? And can we go one step further and actually say no out-of-band authentication credentials required? So these are the authentication credentials to the secrets manager. Can we make it so that we don't have to configure that? And the answer is yes. Obviously, that's why we're having this discussion for certain fairly common types of secrets. Now, just as a quick side note, I've been mentioning security controls a few times, so it's worth a side note to just talk about those. We've listed some of the most common security controls on the screen here. Most people know multi-factor authentication. Just-in-time access is getting more popular these days. That's where maybe I'm a sysadmin and I do have access to SSH to the production server, but that doesn't mean I should be able to do that at any time. I should maybe only get that access when there's a change request approved to make a change to the production server. Anyway, there's a whole list of these controls. And when you're dealing with automated systems, mostly those left two ones are not really applicable. Those are more for human users being involved. Okay, coming back to secrets management. So there's two types of secrets. There's secrets that you export. So these are passwords are a very common case of this. Credit card numbers, social security numbers, if you're using those as secrets, things like that. Those are secrets that you're going to export. But then there's also secrets you don't export. These are most commonly cryptographic keys. And they're used for a wide number of use cases. Authentication. So if you're authenticating to like a cloud endpoint, Azure, AWS, that kind of thing. SSH uses key-based authentication. All those other ones listed there, those are using keys under the hood. There's signing use cases. So code signing, maybe your build server is signing code on every commit. Documents, you'd be signing PDFs, maybe it's assertions like SAML, things like that. Data protection, an application that processes credit card numbers or PII. It's pretty common to see that encrypted before it's written to the database and then decrypted as it's pulled out. So these are all cryptographic key-based use cases, and these all fall under the category of you can do it as secrets you don't export. So we can actually do more things when we don't export the keys. We enable the possibility to do better security when we enable that architecture. So what does it look like? Basically, the idea is we're going to remotely use the secret instead of exporting them to the application. And what this will do for us is it means that the secrets will never leave the secure central management. Now, if you want to go full secure, there's actually dedicated hardware for this in the form of hardware security modules. But if you prefer virtual, those solutions exist as well. Basically, the idea, regardless if you go hardware or not, is that the secrets stay centrally stored and they never leave the confines of that central storage. And so now, because we can get central visibility every time the secret is used, since it never leaves the central storage. And it's possible to enforce security controls every time the secret's used. So let's take a look at what this would look like in an authentication flow. So a common flow is that there's an application and it wants to make use of some resource on a separate server. So the application is going to request access to the resource, and this is going to be a common challenge response handshake. So the server issues an authentication challenge to the application. And basically the application needs to sign that challenge and send back the signature. And then the server verifies the signature and, and knows that the application or user is authenticated. Now, in this case, the application is actually going to authenticate to the session manager and forward, in this case, the hash of the authentication challenge to the secrets manager. If the secrets manager is backed by a hardware security module, it'll then further offload that to the hardware security module for signature. And then it'll send that back to the application. And then the application sends that to the server. The server validates that. And if everything looks good, the application is authenticated. Now, to the remote server, everything looks the same. Nothing has changed. It doesn't even know about the secrets manager, the hardware security module, or anything like that. It just knows that you successfully completed the challenge response handshake. So lines 1, 2, 6, and 7 are what are in the common normal today usage of challenge response handshakes. Lines 3, 4, and 5 are what we tweaked here that the remote server doesn't need to know about. But by doing this, we're able to better protect the secret. And at step 3, we could actually enforce additional security controls at that part. So let's say we wanted to turn on multi-factor authentication. Again, that's something you would do usually for human user systems. But let's say that that's what we wanted to do. The secrets manager can enforce that on the application or the end user at that time without the remote server needing to do it. And that way you get the byproduct of enforcing the security control of MFA in this case, when the application tries to access the resource, even though the resource server did not enforce that control. Maybe the resource server doesn't have the ability to enforce that control. It's an older system, but we can still layer that in. So here's an example that these first 2 examples are going to be shown as human user examples. We're doing that because they are more visually appealing. When we go to the automated systems, it's more command line driven. So I'm going to start with, it's going to be an SSH and a mutual TLS example. And we're going to show how we can layer in multi-factor authentication and just-in-time access without tweaking any clients. and without tweaking any servers. Just everything is remaining as is. All we're doing is offloading that secrets to the secrets manager and remotely using the secret. Okay, so we're showing the key we're going to use to authenticate that SSH one. Here we are using WinSCP to authenticate. And we're able to connect successfully. So we're now going to take that key that we use that's centrally stored in the HSM, and we're going to disable it. So now it should no longer be able to authenticate. There's a retry mechanism in the background, and there we go. We're no longer able to authenticate. And that's kind of how you can start enforcing that just-in-time access sort of capability. So now we reactivate the key. We're also going to turn on multi-factor authentication. So keep in mind, this Linux server we're SSHing to has no concept of multi-factor authentication. It doesn't have a PAM module or anything like that. But we're able to enforce this. You'll see we're prompted for MFA here. In this case, we're using TOTP codes for MFA. And as soon as we complete that, we're able to authenticate. So we're able to transparently layer MFA in, even though the Linux server didn't support it. Now we're going to do the same exact thing here with mutual TLS, just showing another example of doing this. So we're trying to authenticate to a service with a client certificate, and there we go. We successfully did it. And again, the private key is remotely stored in the secrets manager. Now we disable it. This is exactly the same as what we did in the SSH case. And this time it should fail. Again, there's a retry mechanism, and there we go. The key is disabled, therefore we cannot use it. And so we are not able to access it, sort of showing how you can do just-in-time access. And again, now we're going to turn on MFA. So exactly the same as what we did with the SSH example. And when we try to authenticate using the key, we're prompted for MFA. Go ahead and complete it, again, doing the TOTP codes. All of this is possible because we don't export the secret. If we exported the secret, we couldn't enforce these controls. And there we go. We've successfully completed MFA and logged into the app. And so we didn't have to, put a PAM module on the Linux server or recode the web application to support MFA. In fact, the web application and the Linux server have no knowledge of MFA. We transparently or automatically push those security controls down. Now, in these examples, we were using human-based systems, although those could also just as easily been done by automated systems, minus the use of MFA. Let's take a look at some more back-end processing systems, such as tools that are using API access. So in this case, this is an application. It's just a basic application written in Java that's using the standard Azure SDK. And we are authenticating to Azure and then going to do some basic command line. It's going to pull some information down from Azure. So we're using a remote key, again, to do this, to do the authentication. That was the key we showed on the screen there. And there we go. We connected and our Azure application succeeded. So we can even see the audit history of every time the key was used. That's what that was showing right there. And now this time we're going to go ahead and disable the key. It's going to look very similar to the last two demos. And now when we run the application, it should fail because we can't use the key, so we can't authenticate to Azure. And there we go, we get the failure. Okay. So, and even though this is imitating a back-end processing system, just to show that it's no different than anything else, we're going to do a multi-factor authentication. Again, this wouldn't make a lot of sense for a back-end application, but it does show how we can layer in security controls, even though the application was never written to handle MFA. There we go, we're prompted, should look very similar to before. And again, the application is still waiting. And now it's connected and everything succeeds. So we're able to do all of this. It doesn't matter if it's an automated backend system, a human user-based system. We can inject these controls in an automated fashion without having to tweak anything. In this case, we're doing code signing. So we're signing code using a key in the backend HSM. Again, we can audit the usage of that key, even though, so the key was never exported to the system, and we're able to use it to sign. And we're going to go ahead and do the disable of that key and show that now it'll fail if we try to run the exact same command, because we've disabled the key and we can enforce that control in real time. And so basically, this just shows that we're able to enforce security controls in real time, but still let tools and applications make use of these keys or secrets as if they were locally stored, except they don't get the raw bytes. They don't get access to the raw bytes. Okay, so what have we done so far? Secrets are no longer prone to theft, right? This is a big one. Because we don't export the secret, it only remains in the secure confines of the secrets manager, which can also be backed by a hardware security module. We are no longer concerned that the secrets are prone to theft, or it'd be a very, very challenging attack. We also get visibility on each time the secret is used. Okay, so as opposed to before, when we only got visibility when the secret was exported. Let's say that in the past, if the secret was exported, but the application was compromised, someone could just take that secret and use it elsewhere as much as they want. We also have the ability to enforce security controls each time the secret is used. We showed a couple. We showed enabling and disabling to do the just-in-time access, and we did multi-factor authentication. And as a byproduct of this new, enhanced security, we can reduce the frequency that secrets are rotated. All right, we rotate secrets a lot because we export them to unsafe places. Now that the secret is, lives and dies in the secure location, we don't have to rotate them as frequently. You can check NIST standards for how frequently keys should be rotated, but they're in some systems you'll see them rotating, hourly, that kind of thing. We don't need to do that anymore. Now, we still have the authentication to the secrets manager, right? We have to authenticate ourselves to the secrets manager before it'll allow us to use the secrets that it maintains. So can we even get rid of that? Can we make it so that we don't even have to manage those security, those credentials? No environment variable injecting my authentication credentials to the secrets manager. And so we're going to talk about something called bootstrapping credentials. And basically, we're going to also talk about what we're calling implicit credentials. Basically, credentials that come with the runtime environment. So the runtime environment or the platform will inject them and for you. And you don't need to set environment variables or configuration files. And these credentials can often be used without exposing sensitive values to the application, right? We still have to authenticate. There's some credentials somewhere, but can we push it off of our plate and onto something that's kind of a sunk cost? It's already there. So the options that are there for application single sign-on with implicit credentials, in the cloud, there's something called the identity document. So for example, in AWS, when the EC2 instance is deployed as part of the metadata service, there's an identity document. There's also on physical machines, there's the TPM, the Trusted Platform Module. There's an endorsement key hierarchy that you can use. It's a little more complicated, but it's there. There are virtual options for that as well. On domain joined environments, you can use Kerberos and kind of have a service account. So there's options to use these accounts or credentials that are already kind of there for you and piggyback off of that. So the AWS EC2 one that I just talked about, that's everyone's moving to the cloud. So it makes sense to talk about that a little bit more. So the basic idea is this identity document, it's only accessible to the EC2 instance, and it's cryptographically signed. I should say, by the way, that this is not specific to AWS. Azure and Google have similar concepts. But basically, the document is only accessible on the instance itself, and it's signed by something that chains up to a certificate that AWS provides. And so if you're running your application on that EC2 instance and you want to authenticate to the secrets manager, you can send, as the first part, the identity document to the secrets manager, who will validate the signature on the document to make sure that it is valid. And then you can go further than that too. You can check that the IP address of the request matches what's in the document. There's some caveats there that it only lists the private IP, but that's probably getting more in the weeds than we need to for today. There's also some caveats about using proxies and all that. And then you can go further than that too. So you can query AWS to check state in real time. You can even send a separate request back to the EC2 instance to verify that to the IP address that's associated with that EC2 instance and see, is that really you talking to me? But basically, you can use this concept for your application to authenticate without having to inject your own credentials in. You don't have to inject your own secrets into the environment. You can piggyback off what's already there. And then there's still the question, okay, all right, so I authenticate as this like EC2 instance. How do I authorize beyond that? Normally you go group-based access, and you can actually just piggyback off security groups and treat security groups as your groups of which EC2 instances belong to, and use that as I guess the parallel to the more standard way that we do group management. And so let's take a look at what that looks like. We're going to use that same Azure application here. Now you'll see we're showing a security group with SG02, all that. And you'll see that that maps to a security group in AWS, right? So this security group has access to the key that we're using to authenticate in our Azure application, right? So right now, we're going to go ahead and run the Azure app, but we're not a member of that group. So we can't use the key, and so the application fails. Now, when we go back to the console, we're going to add that security group to the EC2 instance where that's running. Okay, so we're just adding that security group. So now we are a member of that group, which has access to the key. And when we run the application, it now succeeds. And so basically, we didn't have to bootstrap any credentials in. We just piggybacked off AWS's existing infrastructure, and we're able to use the security groups as the authorization format. Okay, so what's a summary of the benefits of everything that we've talked about here? So secrets are no longer prone to theft. We have visibility and security controls on each time the secret is used, as opposed to just when it's exported. And as a byproduct, secrets don't need to be rotated as frequently. And we can even go a step further if we want to use these implicit authentication credentials so that we don't have to manage any of these. Now, we were obviously using a specific tool, our own, called GaraSign to do all this. GaraSign is designed to do this at scale, protect your keys, and provide lots of granular security controls to do exactly this. And it supports a large number of use cases. I showed SSH, code signing, and some authentication, but it's really any use case where you have cryptographic keys, you want to proxy their access, and enforce controls in real time when they're used. Any use case like that is supported. And we support that across really any client platform, right? Windows, Mac, Linux, Java, you name it. We have all the client integrations to make that sort of seamless approach that we showed before work in your environment. Thank you very much.